Welcome everyone, and as a result of the unusual weather, I was actually jogging at 5 a.m. today. It wasn't so bad, but some flights were cancelled, so we were missing one speaker at our lunch because of the flight being cancelled. So feel free to ask more questions for the other three, and that would make it even more interesting. We just heard a wonderful ITC ITC colloquium presentation by Paul Shellard, and he will also give a lunch presentation about inflation. His talk is about stochastic inflation in general relativity. So anything you wanted to know about inflation and didn't dare to ask, Paul would be able to answer. Yeah, you can connect your laptop and I'll just present the others. The second speaker will be Pier-Emmanuel Tremblay from Warwick. Where is he? No. Oh, here he is. Thank you for getting here as well. And he will speak about the significance of a volume-complete sample of local stars and white dwarfs. And finally, we'll hear from Xiaojing Lin from Steward Observatory in Arizona. Here she is. And Xiaojing will talk about Census of LyA escape at redshifts 5 to 6 with spectroscopically confirmed H alpha and Lyman alpha and its implications for reionization. Thank you. So we'll start with Paul. From the other Cambridge, I should say. Yeah.
Okay, thanks very much for giving me the opportunity to speak again. I'm very excited about this work on stochastic inflation and general relativity. We're putting it in a much more general framework than the usual stochastic inflation, which makes a lot of approximations. This is work with my student, Ha and Lya, and also it's a long-standing interest of mine with Gerasimos Rigopoulos, who's a collaborator on this and co-supervisor. So we're interested in the origin of quantum fluctuations. That's in an inflationary context, but that's all linearized theory. We want to go to the next stage and look at the interactions. What indicators are there of the type of inflation that we've got? You know, what's going on here? And we need to go to the next order for that. Okay, so quantum field theory in curved space-time works very well, but it misses scenarios. For example, where perturbation theory breaks down, you can have non-perturbative interactions which leave strong non-Gaussian signatures, which is my primary interest. But if you have full nonlinear gravity, you can also look at things like primordial black holes. And so we're looking at realistic detectable scenarios that might be observationally tested in the next few years. So stochastic inflation is a long-established subject area, and it focuses on scales beyond the horizon which behave classically, but previous versions of stochastic inflation have a lot of degrees of freedom missing, and they simplify GR. They generally throw away derivatives and use the super horizon separate universe approximation. So this work formulates stochastic inflation in full GR. Okay, so what we start with is the ADM formalism, where we time slice space-time, okay? And these parameters, the lapse and the shift, show us how our coordinates change between these two time slices, okay? And, they're sort of our gauge choice for general relativity. So our variables, which are very important, are our scalar field, which is going to be driving inflation, and the extrinsic curvature, which is telling us how the universe is behaving between these two slices, how it's expanding or collapsing. And the extrinsic curvature is really what we're interested in. The trace of that tells us how we're compressing or expanding. Okay, so this is the Einstein-Hilbert action. Let's vary it and overwhelm ourselves with lots of equations. Okay, so here are the field equations for the scalar field, and here's this trace of the extrinsic curvature, which is telling us about nonlinear gravitational collapse and expansion. Okay, this is going to be the Hubble constant very shortly, and variations from that are telling us what nonlinear gravity is doing. Okay, so we're not so interested in the trace-free part. Okay, and then we've got these constraint equations which we have to solve, and which will be preserved. So let's look at the interpretation of this. Let's go to background inflation. And in that case, we've got a homogeneous, spatially isotropic universe. And the Kij, you see here's the Hubble constants appeared. It's just a third of that trace of the extrinsic curvature, right? And so then we get the basic equations of the Big Bang cosmology, the Friedmann equation, the Friedmann acceleration equation, Ray-Choudhury equation, and then we've got the equation of motion for the scalar field, which will drive inflation. All right. So that's what happens. We put ourselves on a potential up here. We've got a potential driving everything. Puts us approximately in de Sitter space with variations from that shown by slow roll parameters. Now we want to get the linear perturbations included. So we have our perturbations here. And so we perturb those original equations. Okay, so we've got our background scalar field turns into a perturbation here. And then we've got the usual cosmological perturbation theory. So this is the full nonlinear GR metric, and then we're going to linearize it. Those of you familiar with perturbation theory will know about these Newtonian or Bardeen potentials and so forth. Okay? We're going to stick to the scalar degrees of freedom for simplicity at this stage. So here are the equations. This linear perturbation theory. I'm not doing very well for a 10-minute talk, am I? It's getting very, very complicated. Here's the thing we're interested in, this sort of nonlinear. This is the trace of the extrinsic curvature. Okay. And but this, remarkably, there's only really one degree of freedom here, and that's shown by Sasaki and Makhanov. If you write down this curvature perturbation, which combines the sort of metric perturbation, that's the sort of curvature of the slice, and you add the scalar field, then you get this 1 degree of freedom, and everything collapses into this one equation. And this is the equation you solve, you quantize, okay, and that's where the fluctuations come from in inflation, this Bunch-Davies vacuum, okay, with this well-defined behavior as you go back to infinity, minus infinity in time. Okay, so that everything is being sourced in this universe by perturbations to this curvature perturbation. And so what's happening is we have these fluctuations, and then they're crossing the horizon. They're getting imprinted in the classical space-time. Okay, so during inflation in co-moving coordinates, the Hubble radius is shrinking, and so fluctuations are becoming classical when their wavelength falls outside the horizon. Okay? And so traditionally, this is the way stochastic inflation works. You have your horizon shrinking like that, and then more and more fluctuations are being imprinted on the classical space-time at smaller and smaller scales as time goes on. Okay, that's the idea. And this is usually done in this sort of separate universe approximation on super-horizon scales. So we have to coarse grain between these classical scales and the quantum scale on the small scales. And so imagine we have this nonlinear equation that we're starting with. General relativity is nonlinear. So imagine this is just schematic. So we linearize it, okay? And then we quantize it. Okay, that's what we've done with this already. And then we say, but this is really, this quantum operator has become classical. We replace it with a stochastic distribution. All right? So that's the classicalization. Okay, now we operate and do this with a window function, which is expanding, in proportion to the Hubble radius. Okay, so here we have the equations. Okay, perhaps I should have just emphasized that over here. Here's our window function, and here's our perturbation. This is going to be entirely determined by the quantum fluctuations for that curvature perturbation that I've already mentioned. Okay, so now we go back to the original nonlinear equations. Okay, and we coarse grain them all in the same way. The left-hand side is classical GR above a certain scale, and the right-hand side is this linearized version, which we now know can be written entirely in terms of all these source terms. It looks very complicated, but all these source terms reduce to this 1 degree of freedom, this curvature perturbation. Everything can be expressed in terms of R and this window function. Okay? And so this is the full general relativistic manifestation of stochastic inflation without making the separate universe approximation, without throwing away gradients or anything. So it's also gauge independent. We've made no gauge choice. The constraints are satisfied automatically. It's long wavelength, but we choose where we put the window function. And we can take the separate universe approximation. We get exactly the same equations as Starobinsky would have got. Okay, so now that's general relativity. The ADM formalism is not very good for numerical relativity because it's not hyperbolic. And so in numerical relativity, you have to convert your equations into this BSSN form, which is well behaved. It's a good Cauchy problem. Okay, so that's what we do. We have a dictionary between what cosmologists use in their perturbation theory and what black hole numerical relativists do. And so that's what we do. And so that's fairly straightforward, but the complexity is growing. But, and then we choose a gauge. Now, in numerical relativity, they're always worried about singularity avoidance, but we don't have to do that. We can just choose a lovely synchronous gauge for cosmology and solve the Mukhanov-Sasaki equation to put all our source terms in here in the correct form. Okay, so the context, we put this into a code that we've been developing in Cambridge and the UK called GR Chombo, which we're converting now to GR Teclin to put it onto GPUs. And so that's, it's oh, I see, I hear I've run out of time. But anyway, I'll just flick through some quick slides. That, so this implementation, so we've written the paper about the methodology, the implementation we're still working on, but you can see here we have sort of solved the background equations. They're very simple, you just solve them in Mathematica. But then we've extracted the same variables from the numerical relativity code, and our inflation works perfectly. Okay, so this is the homogeneous case. We can put wiggly perturbation, a wiggly potential in, and we still get perfect results. Our constraints are satisfied just automatically, just by the procedure that we've created. The Sasaki-Mukhanov variable provides those solutions, even when we have a wavy potential, which makes slow roll less obvious. And so then we look at the evolution of the perturbations. I don't know if they're going to evolve nicely. Most of them freeze on super horizon scales, but obviously the scale factor is still growing rapidly. Okay, so that's the stage we're at. We've got a particular ultra-slow roll exemplar that shows how non-Gaussianity grows very rapidly in certain circumstances during inflation, and we're going to use that to test the theory. So this is our expectation, because we can just take what we're doing and turn it into separate universe approximation and solve it very quickly. But we want to find if we get exactly the same results from the numerical relativity code. And notice the non-Gaussianity here. This is originally a Gaussian, and it's got kurtosis and skewness in it now. Okay, so that's the situation. That's where we've presented this way of doing stochastic inflation in full numerical relativity, and we should be able to address some of the outstanding questions like, in principle, what happens when primordial black holes form, when quantum fluctuations get very large. But our primary interest at the moment is looking at higher order statistics. So we will be analyzing the output from this numerical stochastic inflation to look for the bispectrum in particular. So that's the end. Sorry, I've run over.
Thank you, Paul. This is very interesting. So one of the benefits of inflation is that it's supposed to give us a homogeneous, nearly homogeneous anisotropic universe, right? That was the beauty of it, starting from the causally connected region, ending up with that universe. But you are starting, your starting point is actually from a synchronous gauge, which assumes that indeed there is no big variation in the time coordinate. So, I mean, my question, how do we know what was there before inflation? Because in principle, the synchronous gauge may not be allowed if the universe was quite inhomogeneous and anisotropic to start with.
Right, right. You're always asking difficult questions. But my attitude is to start simple and work from there. So I'm not addressing the sort of chaotic inflation. So some people are using Jia-Chombo to look at how likely it is to get a homogeneous universe from random initial conditions,
Right.
you know. And so they set up some sort of bunch of eigenfunctions with, you know, I don't know how they work out the measure, you know, it's a very imprecise subject. But we're just looking at, suppose we do have a smooth universe, we're looking at the perturbative effects around that and how those perturbative effects would manifest in the bispectrum and trispectrum. And so how we could identify which type of inflation had created the fluctuations. So just the next order. So indeed we have simplified initial perturbations, but I think this code could, in principle, start to address those sort of issues. Of course, you know, we're putting in perturbative quantum fluctuations, so you have to keep the quantum fluctuations very small, otherwise your approximations are in question. But certainly this could also look at the question of eternal inflation. Sometimes your fluctuations send you up the potential rather than down the potential, and so inflation continues forever. So there's lots of possibilities here, but we're actually trying to focus on what's observationally testable and working around where the light is shining, you know, the street light, as you pointed out.
You're down to earth.
Yeah, that's right. That's
But
right.
you still are trying, perhaps in the future, to resolve primordial black holes, which would be highly nonlinear.
Yes, that's right. That's interesting, isn't it? Yeah, because something like slow roll, ultra slow roll inflation can end up creating very large perturbations, and then you could follow them into the nonlinear regime. Of course, we've thrown away all the singularity avoidance stuff that numerical relativists have. One would have to put them back in to worry about, you know, stopping your code crashing when a black hole forms. Yeah.
Comments? Go ahead, Shinga.
Yeah, so in this stochastic approach, how do we implement different vacuum? For example, non-bound shavings or non-Gaussian?
Well, yes. First things first. We're implementing Bunch-Davies vacuum, and satisfying the constraints, and then looking at what the gravitational effects then, how they distort that spectrum over time. So that's a very interesting question, how we could put in excited states. Yes, so I think I probably should ask you, actually. But what's also interesting here is that we don't need to just put in the linear approximation. We can, in principle, put in the next order, the one-loop corrections to the original spectrum of fluctuations. And so that's something we're looking at, because we know from a particular given theoretical bispectrum that you, say, predict for your particular inflation model, we know how to create initial data with exactly that bispectrum. So we could, in addition to the power spectrum of initial fluctuations, we can input the next order. So that's something we're exploring. And the other thing is we don't have to do this on super horizon scales. We have all the gradients there. We can push it right back to early times and do sub-horizon perturbations, which might sound incorrect to you because you're classicalizing essentially your fluctuations on a sub-horizon scale. But when you look at the actual approximations you're making, a lot of the dominant evolution actually on sub-horizon scales is certainly for slow roll inflation is classical. And so the quantum effects are due to commutators involving the velocity, but the velocity is very, very small. And so that, you know, we can do better than sitting well outside the horizon, introducing these fluctuations. That's my belief. You can challenge that.
I can tell that Mark Hertzberg has a question. Mark?
I do.
You better have a
I
question.
better come up with one. Okay, maybe a question is, so I guess if you do quantum effects, there's some UV problems, you just cut off it. I mean, yeah, what do you do with the UV spectrum, especially since you're including some horizon levels?
Yes, but in our simulation we have a limited dynamic range. You know, we have a particular length scale, and then the grid resolution sets a limit. Yeah.
Sub-horizon modes, your spectrum becomes kind of Minkowski.
Yes, that's right.
So
Yes.
the Minkowski modes have a lot of fluctuations in them, don't they?
Yes,
so it's
that's
not
true.
Totally obvious that you can handle that in this prescription.
Yeah, that's not obvious. And in the normal stochastic inflation approach, you have a window function which doesn't introduce those at all. It would be just if what I was saying, we push that window function inside the horizon, then we would have to deal with that problem. Yeah. So I don't have an immediate answer to your question.
Okay, last question. Go ahead.
So I just wanted to clarify those red terms that you had in your equations.
They're the source terms, you mean?
The ones where you integrate out the short modes.
That's right.
So that's like an exact parallel, like of the usual white noise in Starobinsky's stochastic inflation.
That's right. These are Langevin equations. There's a noise term on the right-hand side.
So
Just a fluctuating classical field, you know, with certain statistics, Gaussian statistics, and you just choose a bunch of random numbers and imprint that signal into your space-time, satisfying the constraints, and then you carry on evolving your nonlinear equations on the left-hand side.
Presumably your assumption about Bunch-Davies is going into what kind of distribution that's drawn from.
Of course, yes. So this is entirely standard inflationary Bunch-Davies vacuum being introduced on the right-hand side all the time. So at every time step, yeah.
Right. So my related question to this was, like it's in normal, perturbing, just having like a scalar field or a rigid de Sitter background. The nonlinearities kick in when you relax the potential, in a sense, like when you take a massless limit or something, and the wave function of these long wavelets more spread out. So where exactly are the nonlinearities coming in over here?
Well, a good example is the ultra slow roll case where you sort of stall the scalar field as you're going along. And so where exactly are the nonlinearities coming in? Well, that's a very good question. So we haven't done these simulations yet, but you know, the primary mode for nonlinear gravity will be this trace of the extrinsic curvature. So I would expect these sort of source terms here to be driving peculiar behavior.
We need to move on.
Yeah, sorry. All right.
Let's thank for again.
Okay.
Hello everyone, should I start? I'd like to talk to you about the significance of a volume complete sample of local stars and white dwarfs. First question is, what is the best sample of stars? There are certainly various answers for that. One of them is an optimized, clever selection function with proper statistics. It could be, for instance, using the same number of stars for each luminosity bin. So those methods are well tested, but I also want to compare that with a volume sample of all stars within, say, X parsec of the sun. So why would we do that? These volume samples might have many stars that are very similar, so we add up stars that may not be that different, but at the same time, building a volume sample of stars essentially guarantees you to get the brightest examples of every type of star, disk, or planet that you want to study. And very often, that's the best archival data that we have available is for these brighter objects, and also are these objects that will feature in your volume limited sample. Another reason is that, well, I think most will know this already, but low luminosity objects have a low energy loss rate, which means they are long-lived. So volume samples are very useful to study old white dwarfs, old stars, cool M dwarfs. And in recent years, the 100 parsec sample has often come up, especially the Gaia sample of local stars. And this is a round number, but it's not fully arbitrary, because this is where we can have the full luminosity function for white dwarfs and the same for M dwarfs. And for example, this is the only volume where we can get white dwarfs with a cooling age larger than 5 giga-years. So if we want to study the full Milky Way evolution, that's really a sample that is important. One example of such volume sample is the official Gaia collaboration sample of about 300,000 stars and white dwarfs within 100 parsec of the sun. And just looking at the raw numbers from that sample, we can immediately see that there are 7% of white dwarfs, while 97% of all stars in that sample will eventually become white dwarfs. So that already tells you about the age of that population. And with more detailed modeling, we can extract from that the stellar formation rate for that sample. We can also extract the initial mass function. All of those will set the fraction of the stellar population that are white dwarfs at present day. Another feature of having such a volume limited sample is that you have examples of quite bright stars with a very faint white dwarf companion, and you can use that to calibrate stellar age, both for main sequence stars and the white dwarf companion. So to go towards those goals, we have started a spectroscopic follow-up of, so far, all white dwarfs within 40 parsec. That's about 1,000 objects from Gaia that are released 3. This was the work of one of our PhD students, Mary O'Brien. And here, this is just the result in terms of all white dwarfs within 40 parsec with their masses, their temperature, with combined spectroscopic and photometric Gaia fitting, and we also have their spectral types. I won't get into all the details of that distribution, but just want to mention that one application is to inverse that white dwarf mass distribution into initial stellar masses. So we call that the initial main sequence to final white dwarf mass relation. If we use a volume limited sample, that's fairly straightforward in the sense that we start with the white dwarf mass distribution, then we assume a few things, including the saltpeter initial mass function in that case, constant formation history, and standard main sequence lifetimes, and then we obtain this relation for the mass loss following the main sequence to the white dwarf. And the mass loss is significant. It's between 50% and 80% of the initial mass. I want to mention that this work was done by one of your local fellow, Tim Cunningham, who is in this room. Another unexpected thing we found during this spectroscopic follow-up of local white dwarfs are very old and cool metal-polluted white dwarfs, for which the first time we found evidence that they have accreted lithium and potassium from rocky planetesimals falling into the white dwarfs. The diffusion timescales of those metals are quite short, so we have strong evidence that those are from pollution from debris in the white dwarf atmosphere. And one of those objects in particular was observed and characterized by another of my PhD student, Abby Elms, and it happens to be the reddest and coolest known white dwarf. Just to mention, it's quite faint. It's 20 magnitude at 28 parsecs, which shows that this is very close to the Gaia magnitude limit, and for some of the oldest objects in our neighborhood, we can only see them up to about 30 parsec. But most importantly here, we detect sodium, lithium, and potassium in a somewhat low signal-to-noise spectrum. Hopefully, we get better data soon. But what is surprising with those is that this particular object is very much enriched in both lithium and potassium. This is the observed white dwarf here. And we can compare that to other white dwarfs polluted by planetary debris and also objects in our solar system, such as continental crust. Here we have some chondrites, bolt Earth, and the sun is depleted in lithium, so it's at the bottom here due to nuclear burning of lithium. And this object is very peculiar, and if we assume that it might have accreted some time ago, and now we see the settling of those metals in the atmosphere. If we go back in time, we actually get something that is even more potassium-rich, which doesn't solve. It's not giving more insight into what could be the origin of that object. So we are faced with three scenarios for these very large enrichment in lithium and potassium. The first one that has been mentioned in the literature is that it could be primordial gas enriched in lithium. I feel this is unlikely. First of all, this white dwarf is old, but not that old. The cooling age is about 10 gigayear, and the kinematics are consistent with old disk population. So it would be a bit surprising that we see evidence of primordial lithium in such an object. White dwarfs don't have information on the original stellar metallicity, so we don't have that information to pinpoint the age. Also, potassium is not primordial, so that would not explain the very high potassium abundance. Another explanation is that we have some unknown geological process going on there, explaining the peculiar rocky abundances. And finally, it could be a white dwarf effect, so something we don't understand in terms of chemical mixing and abundance enhancement in white dwarf atmospheres. That could be the explanation. But that process would need to act only in that particular white dwarf and not in the thousands of others where we see rocky debris that have Earth-like composition typically. So that's all from me. I think the conclusion, at least for this problem, is that we need more data. Thanks.
So, Pier-Emmanuel, is it diffusion that you're thinking that could somehow lead to such an unusual composition? Or would you think that geological processes could be even more effective? What's your hunch?
I think we must be cautious about atmospheric processes in white dwarf. It is the oldest and to some degree one of the most exotic white dwarf by itself. Oldest means we have a rather dense atmosphere. It's still surprising that white dwarfs that are just marginally warmer and younger do not have such extreme lithium and potassium abundance. So really something special must be going on in that white dwarf, could be due to magnetic fields. But I think more work is needed to understand better the extreme cool, dense white dwarf atmosphere before we are confident that there is a geological process going on there. So I think we must be cautious.
Thank you. Comments, questions? So, at any event, this census that you mentioned is quite helpful in figuring out the solar neighborhood and how the element abundances we find in the solar system comply with what we find in our neighborhood, because that may reflect different enrichment processes that took place in different supernovae. And so thank you for describing it, and we look forward to more data as we continue.
Thank you. Thank you very much. Yes.
So may I start? Hi everyone, I'm Xiaojing Lin. I'm a third-year graduate student from Tsinghua University and Steward Observatory. I'm so happy to be here to share with you guys our recent work about the Lyman alpha escape fraction at redshift 526 and its implication for the reionization. So this work is in collaboration with my supervisors in Tsinghua University, Zheng Cai, and my supervisor in the Steward Observatory, Xiaohui Fan and Feige Wang, and also Feng Wusun, who will come to CFA as a postdoc very soon. So reionization is a really important phase transition in the early universe, where the intergalactic medium transitioned rapidly from the neutral to the ionized state. There has been a long-running debate on the main contributors of the reionization. Who contributes the most ionizing photons for the reionization? A popular view suggests that those relatively UV-faint galaxies with low stellar masses are the main contributors. Those galaxies, there are some recent observational evidence suggesting that those galaxies have relatively high ionizing photon production efficiency, even though they have relatively low escape fraction of the ionizing photons. Their huge number density makes them dominant. However, some recent work start to focus on the UV bright galaxies. They argue that these UV bright galaxies, even though they are not the most efficient in producing ionizing photons, and they may be not the most numerous population in the early universe, but they have relatively high ionizing photon escape fraction, so that they can make a significant contribution to the reionization. So if we want to address this question, who contributes to the majority of the ionizing photons, the key is to constrain the escape fraction of the Lyman continuum photons, which is energetic enough to ionize the neutral hydrogen atom in the intergalactic medium. However, it's very unfortunate. It's extremely hard to directly observe Lyman continuum photons at redshift higher than 4. These Lyman continuum photons, once they escape outside the galaxy, they will be quickly absorbed by the neutral hydrogen atoms in the intergalactic medium so that we cannot capture them. But fortunately, the Lyman alpha photons can survive through the intergalactic medium. These Lyman continuum photons and Lyman alpha photons are both produced by the very young stellar population within the galaxies, and they are both sensitive to the opacity of neutral hydrogen and also the geometry of the interstellar medium. So they may share the same escape channel so that we can use the Lambda alpha photons to probe the Lambda continuum. To determine the Lambda alpha escape fraction, we need to detect the Balmer emission lines of high redshift galaxies. But for example, for galaxies at redshift like 5 to 6, their H alpha emission lines are located at about 4 to 5 micron, which is inaccessible by spectra until the launch of JWST. So how lucky we are born in the era of James Webb. The most suitable field to conduct such experiment is the Gustav's field. There is a Trajectory JWST program named Fresco. Fresco uses the wide field slitless spectroscopy of the near cam to efficiently capture the strong emission lines of all galaxies within a field view. So by using the F444W algorithm, we are able to identify the H alpha emission lines of star-forming galaxies at redshift 5 to 6. In the same field, in Gustav's, there are also deep observations of the MUSE, which use the integrated field spectrograph to target Lambda alpha emission from galaxies from redshift 3 to redshift close to 7. So combine the MUSE and the Fresco data, we are able to simultaneously identify the H alpha emission and Lambda alpha emission of galaxies at redshift 5 to 6. We finally get 165 H alpha emitters within the overlap region of the MUSE and the JWST, among which about 53 are with Lambda alpha detection. We stack the MUSE data cube at the wavelength of Lambda alpha and normalize to the H alpha flux so that we can get a median Lambda alpha escape fraction around 0.09. We also obtain a similar median value when considering individual galaxies. We found that this Lambda alpha escape fraction of individual galaxies follow an exponential distribution with a median around 0.1. We further examine how the Lambda alpha escape fraction depends on the galaxy physical properties. Among all the key physical parameters that describe a galaxy, such as stellar masses, UV luminosity, and the ionizing photon production efficiency, or something like that, among all these listed physical parameters, the dust attenuation, which is the EB minus V here, and the UV slope, beta here, are the two most crucial factors to regulate the escape of Lambda alpha. The two parameters show very tight correlations with respect to the Lambda alpha escape fraction. And this correlation can be well described by the analytic formula. So the dependence of Lambda alpha escape fraction on the galaxy physical properties shows a very similar behavior to the escape of Lambda continuum photons. In particular, the slope of Lambda alpha escape fraction versus beta, which is the green line here, is almost identical to that of Lambda continuum photons, which is the red dashed line here. We simply scale the Lambda continuum escape fraction versus beta, which is measured for the local Lambda continuum leakers. We scale this relation by simply multiplying the relation with a constant factor. We found that their slopes are the same. The same slope indicates that the physical conditions that favor the Lambda continuum photon leakage will also facilitate the escape of Lambda alpha. Also, the beta is also thought to be the best diagnostics for the leakage of Lambda continuum photons. So the identical slope here also implies that the Lambda alpha escape fraction could be proportional to the escape fraction of Lambda continuum photons. So how can we use the similarity between the Lambda alpha and the Lambda continuum escape to constrain the reionization? Typically, people calculate the total ionizing emissivity for the reionization contributed by a population of galaxies, for example, fainter than a specific UV luminosity. They calculate this by integrating the Lyman continuous scale fraction times cosine ion. As a reminder, the cosine ion here is the ionizing photon production rate per UV luminosity. They integrate this quantity along the UV luminosity to the very faint and limited magnitude here, so that they can get the total ionizing budget. Let's simply substitute the Lyman continuous scale fraction here to be the Lyman alpha scale fraction, so that we can still get a relative fraction of the ionizing emissivity when we compare to the total ionizing budget. To do so, we first measure the Lyman alpha scale fraction times cosine ion as a function of the MUV. So this is a good linear relation in the log space. We then integrate this quantity along the UV luminosity function. We found that about 72% of the ionizing emissivity, at least at a ratio 5:6, can be contributed by the galaxy fainter than UV magnitude around -16. If we set the limited magnitude to be the minus 13. And the fraction becomes over 90% if we set the limited magnitude to be -10. So it implies that the UV faint galaxies is likely to provide the majority of the ionizing photons to reionize the universe. Well, I have to say it remains a worth testing scenario with future observations, especially future observations on the faint end and towards higher redshifts. Our experiment here least demonstrates the feasibility of using Lyman alpha escape fraction to constrain the reionization. So here comes a summary. The main conclusion might be we find that the Lyman alpha and Lyman continuum photons can be regulated by the similar physical processes. And we can use the Lyman alpha escape fraction to constrain the total ionizing emissivity for the reionization. And based on simple assumption, we find that UV faint galaxies is likely to be the main contributor. Thank you very much. Questions are welcome.
Did you compare to quasars at all at those redshifts? Are quasars negligible in terms of the UV output?
So if you mention the luminous quasars with
all
the quasars,
yeah.
including AGN.
Including AGN.
So in this work, we mainly focus on galaxies, but actually we discussed about whether the quasar or AGN can be the main contributor. So for the quasar, I mean the luminous quasar, the typical supermassive black hole, for those quasars, people working on the quasar and the quasar luminosity functions find that the quasar it's possible not to be the main contributor due to their relatively low luminosity, low number density. So if you want me to give a number, if I remember correctly, so the quasar will contribute the ionizing photon less than, I think it's 7%, yes. And for the low luminosity AGN, for AGN, so firstly, the recent work focused on the high-res AGN. We are mainly discuss about this, that's obscured AGN with relatively low mass supermassive black hole. For this type of AGN, people argue that because their UV part might originate from the galaxies, so we can still count this kind of population to be like a galaxy contributed, because this is still the UV photons from the galaxy. And for the AGN, exactly the black hole component within this kind of galaxies, if these AGNs are highly obscured, it's possible that they cannot contribute much photons. So, but Yeah.
You will guess it's stars that are reionized the universe based on the numbers you mentioned.
Yeah.
Yeah. Okay. Any other comments, questions? It looks like everything was clear.
You used my question.
Oh, I used it. Sorry about that. I mean, once we have chip in our head, then we can tell what each of us is thinking. I don't have it. So let's thank Xiaojing again and everyone
Yeah, a lot of well, there will be papers. It will say actually the key papers are already available on the Relativity. Yeah, but yeah, there will be key papers. I mean, there will be a bunch of but yeah, the key papers are still long because they summarize.